Okay, we're on page 2 of the chapter 9 worksheet. In example 2, it says, what is the hybridization of the nitrogen atom in NCl3 and the xenon atom in XeF2? So if we're looking at NCl3, nitrogen is your central atom. You've got 3 chlorines attached to it. Nitrogen is in 5A, chlorine is in 7A. 5 plus 21 is what? 26. Right? Okay. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So there's your Lewis structure for NCl3. Now, if we're determining the hybridization, remember the shortcut that you can use is look at how many things are on that central atom or the atom around which you're determining the hybridization. So remember, we're going to begin with S. So we have an S, a P1, a P2, and a P3. So the hybridization of the central atom is sp3. Okay, and you will often see this 3 written either as a subscript or a superscript like in your textbook. Now, if we're doing XeF2, what's my central atom? Xe, and then we're going to have a fluorine on either side, and then Xe is in 8A, F is in 7A, so I need to determine how many electrons I have total. 8 plus 14 is 22. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. I have more electrons than needed to satisfy the octet rule. You put the extra on xenon, and that's totally acceptable because it's in the 3rd period or below. And here we've got 1, 2, 3, 4, 5 groups. So S, P1, P2, P3, and then we have a D. So the hybridization on the central atom is sp3d. Easy enough? Okay. Now, example number 3. What orbitals in the CH bond and the CCl bond of CHCl3 overlap? What kind of bonds form? Okay, now for this one, I'm going to do this over here. CHCl3 is going to look something like this. Okay, there's your Lewis structure. And if I'm looking at the CH bond, which is this, okay, hydrogen has an electron in 1s. Okay, so that means that for hydrogen, in 1s, you have 1 electron. So I'm drawing an orbital diagram to represent the electrons so that you can tell which orbitals are going to overlap. Now, if I'm looking at carbon, carbon is, if I'm just looking at carbon's valence shell, okay, carbon has 2s and 2p. It has 2 electrons in 2s, and then it has 2 electrons in 2p. Okay, so those are my orbital diagrams. Now here's where it can get a little confusing. You're going to have an overlap between I'm trying to determine how I want to tell you this because I don't want to confuse you. Carbon is sp1, p2, p3. Agreed? For its hybridization. Okay? It is often easier to draw the Lewis structure and determine the hybridization of that central atom first before you explain what electrons are overlapping. Okay? So here we've got 1, 2, 3. And so if I'm looking at my carbon-hydrogen bond strictly, okay, what's going to happen is you're going to bring these together, and you've got sp1, p2, p3. And you're going to have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay? And I'm kind of explaining this. I'm making this more confusing, actually, for you. Let me back up a second. We'll leave this. When you have hydrogen in a bond and they're asking you to explain what electrons are overlapping, you only have to say an electron from the 1s, or the 1s is overlapping from hydrogen with carbon to create, because this bond, it's been a while since we've talked about all this stuff, so just to refresh your memory, single bonds are sigma bonds, okay? So they're more specifically asking, what did you form and how? And so you're going to have an overlap of a 1s electron with an electron from one of carbon's valence shells, okay? And so if you're doing carbon and hydrogen that way, and then I'm asking you for a carbon-chlorine overlap as well, like how did they form this, which is just another sigma bond, okay? Let me draw out your chlorine. Chlorine is 2s. That's carbon. Chlorine is 3s and 3p. So you have this 1, 2, 3, 4, 5. This one electron in the 3p from chlorine is going to overlap this comes together with this, okay? So if I'm making S, P1, P2, P3, which is my hybridization on carbon, then you're going to have your 1, 2, 3, 4. Okay. These 4 electrons in carbon's valence shell overlap with electrons from hydrogen and chlorine to create sp3 hybridization. By this electron overlaps with one of them, okay? And then you have 3 electrons from chlorine overlapping to make it your sp3. Okay? And this is how you get your 4 sigma bonds that form. Okay? And I'm going to do a ton of these. I know, at first it's super, super confusing. Okay? This is nothing like you've done before. So basically I'm taking atomic orbitals. Okay, so the traditional atomic orbitals that you're familiar with, and I'm overlapping them to create a hybrid orbital, which is sp, sp2, sp3, sp3d. Okay, and I do that by overlapping valence electrons. Now, let me try and make this a little less confusing. Let's take a look at the valence bond theory for methane. We're just going to start doing some practice problems, and when I'm done doing practice problems, it should be a lot clearer. Yes?
So, like, how would you answer what orbital means?
So, it is easiest if you draw the orbital diagrams and you explain it using the orbital diagrams. So that way you can see like which electrons are going to overlap. So let me do some more, okay? Because I feel like you need the visual to help you through it. Okay, so here, let's look at the valence bond theory for methane, okay? All right, methane is CH4. It looks like this. The hybridization around the carbon atom, the way that we get 4 sigma bonds, which are single bonds, is the 1s electron from hydrogen overlaps with some of the valence electrons in carbon. And that's how I get this sp1, p2, p3 hybridization on carbon, okay? Now, if I wanted to explain this using orbital diagrams, I forgot to do attendance. I am so sorry. Anna's gone, and Kay Jackson. Anna Lou and Kay Jackson, they're both at band at Brophy. Yeah, they're doing a practice. Both of them told me. Yeah. Okay. Bye. Okay. All right, so this is carbon's electron configuration. Its orbital diagram looks like this. Okay? We are only concerned with valence electrons because the valence electrons are what participate in bonding, right? So what happens is you have 4 electrons in the valence shell for carbon. They're going to overlap with a 1s electron in hydrogen to form 4 sigma bonds. So these are overlapping with hydrogen's 1s1 electron. Okay, so what will happen here is I have 4 hydrogens, right? Since I have 4 electrons here, each one of those electrons goes in its own orbital. And since carbon is sp3, think of it this way, sp1, p2, p3. That's how many orbitals I need to have. I take my 4 valence electrons from carbon, I put 1 in each orbital, and then if I have 4 hydrogens, then what happens is you have a hydrogen overlapping with each one of them. And that's how you form your 4 sigma bonds around carbon. Does that make more sense? Okay. And it's like, you can read this in words in a textbook, but to be honest, until you have the visual, the words don't really mean much. Okay? Okay, so each 1s from hydrogen overlaps with 4 sp3 hybrid orbitals to make 4 sigma bonds. Just so you know, each one of these orbitals is an sp3 hybrid orbital. I simply use this to show you how many orbitals you would need. Okay? Okay, now, why are we talking about hybridization of orbitals? Hybridization of orbitals is a much better explanation for bonding. They're more stable. Okay? Let's turn to the next page. Let's take a look at ammonia. Okay? Let's do valence bond theory for ammonia. Okay, ammonia looks like this. It's drawn for you in your handout. The central atom nitrogen is sp1, p2, p3 for the hybridization. Okay? Nitrogen has an electron configuration of 1s2, 2s2, 2p3. My valence electrons are in the 2s and 2p orbitals. Okay? Hydrogen is just 1s1. Okay? And I have 3 of them. Here's what I want you to know. You have 3 sigma bonds. Okay? And you have 1 lone pair of electrons on nitrogen. Okay? So when you're doing this, what's going to happen is the 5 electrons that are in nitrogen's valence shell are going to go into these sp3 hybrid orbitals. So I'm going to fill them first. 1, 2, 3, 4, 5. Okay? Then you have 3 hydrogens. 1, 2, 3. Okay? These 3 formed your 3 sigma bonds on nitrogen. Okay? And then this right here, this pair, this is your lone pair on nitrogen. Yes.
When we write in the sigma bonds that hydrogens form, like
Yeah.
on a problem, so we would want to fill up like all the spaces.
Yeah. Yeah. And just you would put, you can write this down and then put this into words. Does that make sense? Okay, otherwise it's just kind of overwhelming to do. Yeah.
How do we determine which ones are valence electrons?
It doesn't matter.
Okay.
It doesn't matter. I was just doing 2 separate colors to try and show you.
Well, I mean, like for on N.
Oh. Okay, so with the highest number here in front of S and P. Yeah. Sorry, I thought you were asking something else. Okay, let's go on to water. Okay, for water looks like this. S, P1, P2, P3. Hybridization for oxygen is sp3. Okay, oxygen has an electron configuration of 1s2, 2s2, 2p4. Hydrogen is 1s1. So I have 2 electrons in 1s, 2 electrons in 2s for oxygen, and then in 2p I have 1, 2, 3, 4 electrons, right? So you're going to take your valence shell, and that's going to overlap with hydrogen 1s. So it's S, P1, P2, P3. Okay? You have 6 electrons in oxygen's valence shell. 1, 2, 3, 4, 5, 6. You have 2 hydrogens in 1s, right? With electrons in 1s. So there's 1, there's 2. These 2 form your 2 sigma bonds. And then these are your 2 lone pairs of electrons on oxygen. Got it? Yes.
Will the sigma bonds always be on like the last one?
No. I'm just doing that. If you feel it the way I do, yes. Okay? Okay, yeah.
If you have molecules like sp2, would you just have like 3 instead of
Yes.
1?
Yes.
So when you write out the lone pairs or sigma bonds, it doesn't matter which one.
It really doesn't. It really doesn't. Okay, now let's take a look at example 4. I want you to practice drawing the Lewis structures of BBr3 and CO2 and CO3 negative 2 and telling me what the hybridization is for your central atom. Let's just do that much for now. Okay?
B is one of the exceptions, right?
B is one of the exceptions. Yeah.
Would it be alright to use the double dash shorthand notation for these? Like the...
Yeah. Oh, totally. Totally. No, no, you don't even have to go that far. All you have to do is, draw the Lewis structure and determine the hybridization, okay? I just want to make sure that you can go that far, okay? Because I'm going to explain which ones are overlapping in detail in quite a few more problems. I don't make you do that until your homework on page 6, I think, okay? Okay, so BBR3 is trigonal planar. It's SP2, right? So SP1, P2, boron is an exception to the octet rule. That's why it only has 3 single bonds on it. Carbon dioxide, it only has 2 things on it. It doesn't matter if it's a single, double, or triple bond. This is still considered just like one group, okay? So this would be SP. Carbonate ion, trigonal planar again. It actually has resonance. I only drew one of the structures. It has 3 things on it. This is SP1, P2. So carbon's hybridization is SP2. Okay? Okay, now, so you do 2 and 3 for homework. We're going to go on to hybrid orbitals for molecules and ions with trigonal planar electron pair geometry. So I basically have just shoved as many examples in here as I possibly could. Okay? Just because the more you hear it, the better you're going to get at it. Okay? All right, now, if we're looking at BF3, which has 3 things on the central atom, right? Therefore, this would be sp2 for its hybridization. Now, you tell me, what is the electron configuration for boron? 1s2, 2s2, 2p1. Okay, so this is its valence shell. It has 2 electrons in 2s, and then it has 1 electron in 2p, right? And then fluorine, what is fluorine's electron configuration? 1s2, 2s2, 2p5. So, all right, now, fluorine looks like this for its orbital diagram situation. Okay. So you take the valence electrons in the central atom, and we're taking this 1 on fluorine, this lone in the valence shell. Okay. And since our hybridization is sp2, you have sp1, p2, right, when they overlap. I'm going to take the 3 here, 1, 2, 3, okay? And then I have 3 fluorine. So I take this one from each fluorine, and it overlaps with each one, creating my 3 sigma bonds. And I don't have any lone pairs. Okay, so the central atom has 3 hybrid orbitals. It's trigonal planar. That's how many degrees apart is trigonal planar? 120. So the 3 hybrid sp2 orbitals actually are going to lie in the same plane because this is trigonal planar. Okay, and we never really got into drawing x, y, z axis, but if you think about it this way, your p's, you have 3 dumbbell shapes, okay, in your traditional atomic orbitals for the p's. One is on the x-axis, one is on the y-axis, one is on the z-axis. How many of you have already started doing z-axis in math? Okay, so you know that you have an x and a y-axis, and they're normally on the plane of the paper, right? And that your z-axis makes it look 3-dimensional. If we're doing trigonal planar, I can only be looking at a p that's in the x and the y because they're in the same plane. Does that make sense? So really, the only electrons that can participate are the ones that are there. Does that make any sense at all? Maybe? Maybe not. Okay. All right, let's turn the page. Let's take a look at BeCl2. Okay. All right, you tell me, what's the hybridization on BE. SP, good job. SP. Okay. Beryllium has an electron configuration of 1s2, 2s2. So the electrons that are in the 2s are the ones that are going to participate in bonding because those are your valence electrons. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. So really we're focusing on the electrons that are in the 3p. 1, 2, 3, 4, 5. Okay? So what happens here is this is going to overlap with this. We have sp. I have 2 electrons for beryllium, and then I have 2 chlorines, which means you'll have 2 of these single electrons from 3p. So one goes there, one goes there, and that's how you get your 2 sigma bonds. Okay? This one is linear, right? It's mx2 for its designation. So this would be linear. How many degrees between bond angles? 180. And since these all, these are going to lie along one axis, these are going to lie on the z-axis. X and Y are not going to be occupied. Okay. All right, let's go on and take a look at the next example. Let's go down to example 5. Describe the bonding in PF5 and XEF2 using valence bond theory. Okay, I'm going to have you do that with a person sitting next to you. Draw the structure, do your orbital diagram, explain which electrons are overlapping to create the bonds, and then we'll move on to double and triple bonds, and then we're done. Yeah, draw the structure, find the hybridization on the central atom, and then describe, like draw your orbital diagrams and describe which electrons are overlapping to create those hybrid orbitals. Okay? you get this for the first one? Like that one was okay. Did you understand the second one though? Yeah? So we're good? Anything you want me to explain? Yeah, yeah, okay, so Xe is 5s2, 5p6, right, for the valence electrons. And its orbital diagram looks like this. And so you're going to have all of these electrons, because it's the central atom, are going to go into the hybrid orbitals. Your Xe is sp3d, so I have this many sp3d hybrid orbitals drawn out. You fill them in with the Xe electrons first, which I did in purple. Then you have 2 fluorines, which has a valence of 2p5, and you have this 1 electron from the 2p5. And since you have 2 of them, because they're 2 fluorines, that's what I put here in brown, partnering up with these 2 electrons from xenon. These create your 2 sigma bonds, which are here, and then all of these that are paired up, those create the 3 lone pairs on the central atom. Okay? Okay. All right. You do 4 for homework. Let's go on to double and triple bonds, okay? All right, so anytime they ask you to count up sigma bonds, you're counting all of the single bonds. If you have a double bond, then that second bond in the double bond is known as a pi bond. Sigma bonds have the electrons concentrated like along the axis of the bond, like the middle part between the 2 atoms, okay? And the pi bonds actually have the electron density above and below the sigma bond, and that's what they're trying to show you here in green and blue, okay? You can't rotate about a double bond, and I'm going to explain a couple of things to you. And so let's take a look here. We're using ethylene as our example. So this is carbon. Let's call this carbon 1 and carbon 2. And then these little white attachments on the carbons are your hydrogens. Okay? So on this carbon, I have 1, 2, 3 things, right? It doesn't matter if this is a single, double, or triple bond. That means that my carbon is sp2 hybridized. Okay? So how did we get that? Well, carbon is 1s2, 2s2, 2p2, and then it looks like this. And then you've got your hydrogen, which is your 1s1, right? So what happens is your valence electrons from carbon overlap with the 1s in hydrogen. And since carbon is sp2, you're going to have sp1, p2, okay, your little orbitals. And then you fill them up 1, 2, 3, 4 from carbon. 1, 2, 3, 4. And then you have 2 hydrogens, right? So then you've got 1, 2. I should do this in different colors so you can see it. Actually, let's do this. I have a double bond. Let me explain the whole double bond concept really quick. You have a double bond. That means your valence electrons from your carbon, yes, you fill them singly first. You're going to have, these are your hybridized orbitals, okay? And then you're going to have, anytime you have a pi bond, okay, and anytime you have a double bond, you will, one of them is a pi bond and the other one is a sigma bond, okay? You're going to have what is called an unhybridized orbital. And you're going to have one of the electrons from carbon in that unhybridized orbital. And this is where your pi bond forms. Okay? Okay, so we have our carbons, and you're going to have, we have 2 carbons. But regardless. All right, so you're going to end up getting your 3 sigma bonds from here. And then you're going to end up using this to form your 1 pi bond. Okay, and so remember I have 2 carbon atoms with this, and then I have 4 hydrogens. Okay, turn the page for a second, and I want you to see something. This is showing you what the electron clouds or the electron densities or the overlaps would look like. So these are the overlaps created from your hybrid orbitals, okay? These are created from your unhybridized orbitals, creating the pi bond, which is above and below. Okay, so that's a typical example. Number 5 you do for homework, go to formaldehyde. Formaldehyde they used to put in nail polish. It's used to preserve things. Not very healthy. Okay, yeah.
Wait, so for the one where we were doing the ethylene, do we not have to write in those extra electrons?
I wasn't doing it for the sake of time.
Okay.
But I'm gonna do it. I'm gonna do it here.
Okay.
Okay. Okay. So for this one, you have 1, 2, 3 things. Then this would be sp2 for the carbon on formaldehyde. Carbon is 1s2, 2s2, 2p2. So it looks like this for its orbital diagram. All of these electrons go into your hybrid orbitals, and we have 4 of them. 1, 2, 3. I have 3 sigma bonds in that structure, and I have 1 unhybridized p orbital, which has an electron, which goes on to form my pi bond. So these are going to form your 3 sigma bonds. Okay? And you've got 2 hydrogens. So in 1s, right? So this is going to come over here and give you that. Okay? And then you have your oxygen. Oxygen is 1s2, 2s2, 2p4. So I'm just going to look at the 2p, 1, 2, 3, 4. These 2 from oxygen, or I'm sorry. Yeah. One of the oxygens comes here. Okay? Another one of the electrons comes over here to create your pi bond. Okay, which you have between carbon and oxygen. Okay, so just so you understand, let me make the structure bigger. I have a sigma bond here, a sigma bond here, and when you have a double bond, one of them is sigma, one of them is pi. It doesn't matter which one. Yes.
Oh wait. So are you using the 2s of the carbon and the s?
I'm using all of the valence for the central atom, but I don't when I'm using the ones that are coming in to attach. Okay? Okay, now, acetylene is a triple bond. How many sigma bonds in acetylene? Acetylene looks like this. Sigma. You have one here, and one of these is a sigma bond. Okay? The other 2 would be pi. Okay? So when you're looking at double and triple, one of the bonds in the double and the triple is always sigma. And the rest are pi. Okay? Just a really quick explanation on acetylene. If carbon is 2s2, 2p2, these valence electrons in carbon are going to go into, okay, thank you. All right, so this is sp, right? This carbon is sp, so you have sp. And you have 1, 2, 3, 4 electrons in the valence shell for carbon. But I'm going to need to have a couple of sigma and a couple of pi, right? So these are your hybridized, and then you're going to have your 2 unhybridized p orbitals, because you need to form 2 pi bonds. Okay, and then you'll have your hydrogen come in and your other carbon come in. Okay? Okay, I'm almost done. Let's talk about cis and trans isomerism. When you have pi bonding, you cannot, meaning when you have a double and a triple bond, you cannot rotate about it. Okay? So we get something called isomers, which are substances with the same formulas but different structures. So if you turn and you go to the next page, you will see we have cis 1,2 dichloroethylene and trans 1,2 dichloroethylene. What does that mean? Cis means they're on the same side. Trans means they're on opposite sides. So if we're looking at the structure, these 2 chlorines are on the same side of the double bond. Okay? So if you have a hard time visualizing it, here's what it really looks like. Okay? Same side, cis. Where do they get the 1, 2 from? 1, 2, carbon. 1 and carbon 2, they're coming off of that di because there's 2 chlorines. Trans means they're on opposite sides. So here they are on opposite sides. Okay, so that would look like this. There's your trans. Okay. So you just need to know that double bonds are really restrictive, and there's a lot of energy that has to go into breaking those bonds. Sigma bonds, which are your single bonds, you can have rotation about them. Okay. Let's go on and talk about benzene. Benzene is an aromatic compound. Aromatic compounds have an odor to them. Benzene is C6H6. It's a ring and it's flat, and you can have resonance because the bond moves. So you'll see here these double bonds just move, and then you get this structure, and then they typically just put a circle in the middle to show that. Okay? So you have got this packet for homework. This is due tomorrow, so I can have it graded by Monday, so you can have your test on 8 and 9 on Tuesday. You may.